Okay, I'm recording now. Can everybody hear me?
Yeah.
All right, very good.
Yeah, in here.
All right, so as I said before, we've had some technical difficulties. I had to send 18 individual emails out to people because the Blackboard wasn't working, so that's why we're getting a late start. So I had to do it the hard way. So the lab, if you notice at the very top of the lab, there are two links. The first link is wrong. And instead, you should go to what I have written on the board here. So again, the top link is supposed to be for Hooke's law, the second link for the gravitational force. All right. And so so instead, for the Hooke's law, you put in https://phet.colorado.edu/sims masses-and-springs /latest/masses-springs_en.html. All right, so again, that's what we're going to go to instead of the what's the link that's shown. The second link, the one for gravity, is actually correct. All right, I'm going to erase this. As far as the lecture for this, essentially we talked about, chapter 4, you talk about forces in general, the concept of a force. And again, Newton's second law gives you the concept of a force. Newton's first law talks about the concept of inertia or a mass. Newton's second law says, well, you know kinematics from Galileo, and inertia. I multiply that together. It's equal to the sum of all vector quantities that I call forces. It's a push or a pull. We define in general what a force is. And then Newton's third law says, now that we understand, Newton's second law, we understand forces, but now we understand forces, we know there's an action-reaction couplet to forces. Every action has an equal and opposite reaction. All right. So in the normal force is an example of the Newton's third law of force. When we talked about the equilibrium problem the other night on the exam review, those reaction forces I talked about, F sub x and F sub y, again, those are from Newton's third law. All right. Now that we know about the concept of force, there are certain types of forces. There are certain natural forces in the universe. One type of force would be the following. So let's just say, for instance, you have a flat frictionless surface and you have a wall and you have a spring that's at rest. Okay, it has a natural length L naught, or we'll say X naught. That's its natural length. And then we'll attach a mass to it. The mass M. Now, the spring is going to have what we call a special constant K. K is referred to as the spring constant. And one of the things that Robert Hooke was an English scientist who lived at the same time as Sir Isaac Newton. Now, Sir Isaac Newton, as I said in the past, was a unusual guy in that he probably was one of the most intelligent human beings, most intelligent people in the entire human race. But Newton had all kinds of social issues. And, one of them was he would get in intense rages. He had extreme intense anger. And, when he hated you, he really, really hated you. And they had what was called the calculus wars. He was the first person to, I would say, invent calculus. Well, at the same time, what's funny about life is that oftentimes things kind of come about or are invented at the same time. There's a great physicist and mathematician in Germany by the name of Gottfried Leibniz. And Leibniz invented calculus at pretty much about the same time as Newton. And they had the giant debate where Newton accused Leibniz of stealing calculus from him, and they had a huge debate about who should be credited for calculus. Well, it turns out that Newton won that debate, but it turns out that those who do calculus, we actually use Leibniz notation. Leibniz has a much better notation. Now, Leibniz, like Newton, was probably somebody, they estimate Newton's IQ somewhere in the neighborhood of around 190. The average human IQ is about 100. They estimate Leibniz about the same. So they're both absolute geniuses, many standard deviations above the mean, intelligence-wise. Well, another significant physicist who happened to live in England at the same time as Newton was Robert Hooke. And Robert Hooke was another person that Newton absolutely despised. And so there's stories about Hooke and Newton as well. Hooke was definitely an excellent physicist. No, I mean, nowhere near Newton, of course. But so one of the things that, Hooke actually had several contributions. But one of the things he's known for the most in physics is what's called Hooke's law. And Hooke's law basically is the following. If I decide to compress the spring or stretch the spring, doesn't really matter which I do. What I find out is that, we know that the spring, I'm just going to draw another picture. We know the natural length of the relaxation length or the resting length of the spring is, say, x naught. Let's say I displace it by some amount x. Let's say I compress the spring and I move it to, say, let's say the block comes in, and instead of being out here, we'll say kind of the front, we'll kind of judge things where the front of the block is. Instead, we're moving it by some amount. Let's see, where would it naturally be? So it's been displaced by some amount x. And it works exactly the same way if I stretch it. When you displace a mass on a spring like this, there's a force that pushes back on you. There's a resisting force, and it's given by Hooke's law. So when we displace, a mass on a spring by a displacement x, a resistive force forms given by F equals negative kx. This is called Hooke's law. Okay, now Hooke's law is not really a law of physics. Now I've talked about, laws of physics, this is not one of them because it's not general. I mean, it's true the vast majority of the time, but you might have, for instance, another term. You might have, for instance, like in a rubber band. Rubber bands don't follow Hooke's law. Rubber bands follow something like this: negative kx plus, let's say, some alpha x cubed. That would be like for a rubber band. More complicated. So if you have a mass on instead of a spring, you have a rubber band, you have an extra term. Most of the time, the vast majority of the time, there's only a linear relationship. And that's called Hooke's law. But again, a law of physics, remember, is a behavior that is always true. You know, it's a behavior in the universe that's always true. Well, Hooke's law is mostly true. There are exceptions. That's why it's not a law of physics. We say law, we can say law really in quotation marks, if you will. All right. So that's what part A of our class is going to be like, you know, the first part. And in fact, if I were to stretch by an amount X, it would still be met by Hooke's law. Hooke's law is going to resist. So why the negative sign? The negative sign is a sense of resistance. All the negative says is the displacement's going to the left, Hooke's law is going to go the opposite. It's going to push to the right. Oh, if you're stretching, if instead the displacement is to the left or to the right, the Hooke's law is going to point to the left. The negative sign is just the sign of opposition. All right, it's just saying that it's going to go, Hooke's law is going to be directly opposite to the displacement. All right, now this K is a property of the spring. Another reason why it's not a law of physics is because you have to look up a value depending upon how you made your spring and what your spring is made out of. So one way of figuring out what K is to get help from gravity. So for instance, let's imagine getting some assistance from gravity. So let's instead consider hanging my mass upside down. We'll kind of talk about the y-axis instead. So here's the ceiling. Now I'm going to hang my spring, and I'm not going to put anything on it. And I'm going to realize, well, my spring has a natural length. We'll say, why not? Now I'm going to hang a mass on the spring, and I'm trying to figure out what K is. All right, and so here I'm going to take the same spring and I'm going to hang a mass on it, and it's going to stretch. Hanging a mass that I know this mass. I can measure. I can pick a known mass off the shelf somewhere in the lab, and I can realize, well, what I have now is initially the level of where the spring wanted to sit was right there where I put that dashed line, but now it's been displaced by some amount y. So, well, what do we know? We can apply Newton's second law. We know that this mass has the force of gravity, the weight acting on it straight down. But Hooke's law says, well, the weight is what's actually stretching the spring. Hooke's law says, I want to oppose that by having a force that's opposite. So I'm going to say that it's going to oppose it by, say, some sort of a force given by Ky going up. We can apply Newton's second law. We can say, well, the sum of all forces in the y direction. Okay, what are those forces? Well, you have Hooke's law force Ky going straight up, and you have weight going down, that's negative, and this body is in equilibrium, it's not moving. I put a weight on it and it just lowers where the spring, stretches the spring and then sits still. So given that that's not moving, that means there's no acceleration. So the right-hand side of Newton's second law is 0. And what am I looking for? I'm looking for K. I can measure y, that's the displacement when I have a known mass put on that spring. So let me just solve for it, put mg on the other side and divide by K. And divide by y. So I can actually calculate K, and it's just mg divided by y. I put mg on the other side and I divide by y. So in the laboratory, I can very, very easily determine the spring constant. What are the units of the spring constant? Well, mg, that's a force that's given by newtons. And the distance, displacement, is given by meters. So the units of K, the spring constant, are newtons per meter. Now, again, every single spring has its own constant, depending on how thick the material may be that makes up the spring, how it's wound, and also maybe what the material is. You know, the springs in your, you know, let's say a slinky. If you remember, I was playing with a slinky once upon a time. That spring has a very small spring constant. The springs in your garage door have a very large spring constant. You don't want to mess with those. Those will fly in your face and possibly really hurt you. They're under incredible stress. So again, you know, so the springs in your garage door, very large spring constant. The springs in a slinky, very small spring constant. All right. So again, every spring constant, you have to measure it, or it's a value that's given to you. So you go and do an oscillation lab. You have to go and hang a mat, no math, 100 grams or whatever. I know this mass. Maybe I can double check it by putting it on a mass meter if I don't believe the number. And you shouldn't believe the number. You should measure your own number. Get on a mass meter. There's your mass. Very carefully, you know what gravity is, 9.8 meters per second squared. You can measure the displacement y. You can find k. We're going to do some of that tonight. Okay. The other part of the theory is gravity. Now, one of the things that Newton had in the Principia, as I talked about, was gravitation. That's one of the wow effects, one of the effects that says, I can understand how celestial bodies move. And I have the ability, I have the law that can predict it all the time. That's one of the incredible wow effects that, you know, that really made Isaac Newton a rock star in his own time. And Isaac Newton, you know, was, you know, as the story goes, and I mean, I don't know if it's actually the apple falling from the tree, but, you know, Newton observed, you know, let's say we have an apple tree. And I'm not very good at art. But we have an apple on the apple tree. Okay. And Newton, you know, was, as the story goes, was looking at this apple and he watched it fall. And the apple fell to the earth. So, you know, say it used to be here and it fell to the earth. And he watched it fall. And he understood, because he had incredible physical intuition. He basically said, the force that compels an apple to fall from a tree is the same force that compels the moon to orbit the earth. Now, for people who studied physics for many years, you know, that seems like a logical statement. But you're talking about a guy who made this observation in the 1600s, when there was no physics, or very little. This is an incredible observation. I mean, this gives you the idea that what kind of a genius that Isaac Newton was. When you kind of consider that this guy was thinking like this in the 1600s. And so let's talk about let's kind of understand what Newton's talking about. So we know that, you know, that we know we can measure. We know that the apple fall and all other objects so we know the apple and all their objects fall. Let's write this down better. We know that the apple and all other objects fall to the earth with the same acceleration. G equals 9.80 meters per second squared. I mean, Galileo knew that with his free fall experiments. Newton is stating that this is because of this law of gravitation. So Newton did a lot of observations with, planetary, there are people who are able to do observations like Tycho Brahe, and others. There are astronomers who are making very careful observations of orbiting or like planets. And so Newton was able to understand one of the 4 fundamental force laws of the universe, and that is the following: if there is a body M1, we'll start off with point masses. I have a mass M1, well, this is a spherical body. I have a body has a mass M1. And here's another body, mass M2. And there's a center to center distance D, or we'll say R. Newton said that there is a mutually attractive gravitational force given by, between these two bodies, given by capital G, a constant, times the product of the masses, divided by the center to center distance squared. And that's located in the R hat direction. R hat meaning it's along the center to center line. This is a unit vector. All right. So we know that R is the center to center distance. G is a special constant of the universe. As far as we know, it's the same value everywhere. It's 6.67 times 10 to the negative 11. Very small value. Let's see, what are the units on this? Well, if I cross multiply, I have newtons meters squared per kilogram squared. So as far as we understand, anywhere you look in the universe, you see this very small value. Gravity is very, very weak. It's the weakest force by a lot. I think the electromagnetic force pound for pound is about 10 to the 28th times larger than gravity. Gravity is an extremely feeble force. However, why we know about it is because we see bodies that are so ridiculously large. That's why, that there's a universal law of attraction that says everything that has a mass is attracted to everything else that has a mass. But if I walk around in the classroom with a bunch of students, as I walk past them, I'm not being drawn to them through gravity. I don't feel their gravitational attraction because their force is very small. However, the Earth has a huge mass. Now, the mass of the Earth is on the order of 5.98 times 10 to the 24 zeros, or 22 zeros, kilograms. That is a huge mass. The mass of the sun, that's 1.99 times 10 to the 30th kilograms. That's why you feel gravity from these giant celestial objects, because their mass is so ridiculously big. That's why you feel gravity. But generally speaking, gravity is an extremely feeble force. All right. So let's go back to the apple example. How can Newton know this? Well, let's do another setup. Let's imagine here's the Earth. All right, big Earth, and you're a little mass on top of the Earth. Or, well, this better. So again, you know, that was kind of, we can almost think of a flat Earth to some extent, but let's just say we have a huge Earth. And whatever mass, maybe it's you sitting on top. Okay, so the Earth, as I said, has this giant mass m sub e. And you or whatever has a little mass m. And there's a center of the Earth. So your center is right in this little tiny dinky spot. The center of the Earth is down here. So what would the center to center distance be? Well, that would be the average radius of the Earth. Oh, let's apply Newton's law, second law, or sorry, Newton's law of gravity here. So let's see here. We have well, actually, let's do this. We have the summation. Let's do Newton's second law. The summation of all forces in the radial direction, or we can call it the y direction if we like. Well, what force would that be? Well, the only force that would be operating on this mass right now, you know, as far as working, unless it's a mass we're doing free fall, maybe we're just a little bit above the Earth, we're not feeling the normal force. All right, well, that would be what? That would just be nothing more than G, the mass of the Earth, your mass divided by, all right, so sum of all forces in the radial direction. Again, the only force you're going to feel here is Newton's law of gravitation. So capital G times the mass of the Earth times your mass divided by the radius of the Earth squared. That's the center of center distance. And we're going to say, well, that what's that equal to? Well, that's equal to mass times acceleration. So that's going to be mass times what acceleration? Well, we know that any body that's on the near the surface of the Earth is going to fall at what? G. All right. So again, all I'm doing is I'm applying Newton's second law, and I'm particularly saying, hey, I know what the acceleration is. It's G. It's free fall. Well, let's see what we can do here. We can cancel out these m's. So it turns out your mass doesn't matter. And it turns out that we can actually solve for gravitational acceleration. So we can actually write that G is equal to capital G, that constant, times the mass of the Earth divided by the radius of the Earth squared. Well, let's see. What does that work out to be? 6.67 times 10 to the negative 11 newtons meters squared. Yeah. Write this big numbers. All right, again, G is capital G m sub e, mass of the Earth, divided by the radius of the Earth squared. All right, let's do it. Try this again. Again, the universal constant, 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared, times the mass of the Earth, 5.98 times 10 to the 24th kilogram, and then divided by the radius of the Earth squared. You can look this up. Average radius of the Earth is 6.37 times 10 to the 6 meters. Of course, don't forget to square that. If you work these numbers out, you work this calculation out, you will find that G is equal to 9.80 meters per second squared. So it's no accident that, you know, the acceleration of gravity is due to free fall. That due to free fall is because of gravity. And what this calculation says is the force that causes an apple to fall from a tree is the same force that causes the moon to go around the Earth. And so Isaac Newton was absolutely right. All right. And so again, this is the whole concept of gravitation. In this course, in the Physics 1, Physics 2, there are 4 fundamental force laws in the universe. Gravitation is the first one. That's the only one of the 4 fundamental force laws that we will learn in this class. And then a fundamental force law is a force that is true because an object has a particular property. In this particular case, it is true because the object has a mass. When we go to physics 2, we'll understand the electromagnetic force, or some people call it the Lorentz force. And that's a force that is true because an object has an electric charge. All right. And then there's a couple of nuclear forces, and I'm not going to get into those. But again, there's 4 fundamental forces in the universe, and this Newton's law of universal gravitation is the first of the 4 and the only one that we study in physics 1. So again, this formula, this fundamental force, is called Newton's law of universal gravitation. And, humankind had no knowledge of laws of physics prior to Newton. Okay, the fact that this is always true, the fact that there are fundamental laws of the universe, this law of the universe is always true. It's a fundamental principle, it's a fundamental truth. There is no reason that you can point at. It is a fundamental law. Now, turns out this one you can actually explain with a general theory of relativity. This was something that was done by Albert Einstein, and he published it in 1917. That made him a rock star. Again, another way he overturned Newton. But anyway, as far as we're concerned, it is a fundamental truth. And if you're to go and ask why questions, we stop and say, well, it just is. Now, one could say, well, general relativity, the theory of general relativity is a step lower than Newton's law of universal gravitation. But again, we're not there yet. I'll explain that more in physics 2 for those who want to take physics 2. All right, so let's go to the actual lab. So provided that you have fired up the proper web address, I'm going to share screen here with you. We'll look at this lab. All right, so you should be seeing masses and springs. And so the first thing you want to do, again, this is after you type in that big long web address. First thing you want to do is you want to select lab. All right, so you select lab. I'm looking at the lab here. All right, so I'm going to select it one more time. Need to open it up. So I don't know if it's thinking or what it's doing. There it is. Okay, so there you go. You have a spring hanging from the ceiling. And one of the things we're going to do is, and we're not going to talk about oscillations in this lab. No, that's a later chapter. We're just going to talk about the spring constant, Hooke's law, the force itself. All right. We'll revisit this concept when we talk about oscillatory motion. That's not this lab. All right. So what we're going to do is we have a couple of we have 3 masses down in the bottom, 100 gram, and we have a red and a blue unknown mass. Let's put the 100 gram mass on the spring, and you'll notice that the spring starts going back and forth. Well, how you prevent that from happening is we're going to take what's called the damping coefficient, and we're going to make it into what's called lots. Damping, we'll talk about this when we talk about oscillations, but damping is actually a different kind of friction. Now, the friction we've studied so far is the sliding friction. Damping is the friction within the windings of a spring. Turns out it's proportional to the velocity. Again, don't worry about that, but something that is highly damped does not oscillate easily. Something that has very little damping oscillates back and forth very easily. So we don't want any oscillations. Oscillations, again, is a fancy word for vibration. We don't want that, so we're gonna max out the damping coefficient. All right. Now, what else do we want to do? I'm gonna move this out of the way. We want to click the displacement and the movable line. So we're going to click, we want a displacement vector. There it is. and we want the movable line. We want that a little red line there. Okay, so that just popped on the board. All right, I'm on page 2 of the lab. Now, what we want to do is right now we've defaulted to 100 grams. Now, of course, we really want, so I'm looking at the table on page 2. We want to consider 6 different mass measurements. And so for right now, let's look at something here real quick. I'm going to take the mass off and then pull the mass back off. Now let's look at where the spring is. All right, so the spring, I'm going to get my little red line out of the way for right now. So let's just move this out of the way. All right, notice that the little dashed blue line marks the resting length of the spring. Again, that's the spring with no mass on it. Okay, but I'm going to put a mass that I know. I'm going to put 100 grams on this. What's going to happen is you notice that the green arrow appears. That's the displacement. So now the mass has moved to a new equilibrium point. So it's displaced. So I measure that displacement. That's my y. All right, and so I'm going to go and put the movable line right at the very tip of the arrow. And what I'm going to do at this point is I want to now pull the ruler off of the tool set here. So I'm going to pull this ruler out. And I'm going to try, now this ruler is in millimeters, as it's said in the lab. What I want to do is I want to figure out how big the displacement is. So I never go to 0. I always go and start at, let's say, 10 millimeters, and I just figure out what the value is, and I subtract 10. All right, and so if I look at this very carefully, I see 20. It looks like I don't quite get to 30. Looks like I get to about 27 on there. If you look at where that red dash line is, it looks like it gets to 27. Now, of course, it's not 27. It's really 17, right? Because I have an offset of 10. I started measuring at 10, so it's 27 minus 10. So what I would do is in my so kind of remember that it's 17 millimeters. What do I put in my first table? Let me stop sharing for a sec. Okay, so my first row of the table, what do I put? Well, my table looks like the following. It says mass added in grams. Okay, weight in newtons. And extension in millimeters. All right. Well, what we really want is everything at SI. So if you remember, I hung a 100 gram mass. However, I want to write that in terms of kilograms. So if you remember for a moment, I want to get newtons. So how do I do that? Well, I have a mass that's 100 grams. Okay, well, what's a kilogram? Well, 1 kilogram has 1,000 grams. And so what I really have is 0.100 kilograms. And so what I really want in here, I'm going to write this in my same little cell, is 0.100 kilograms. That's important to me. I really want the value in kilograms. All right. Now, I write that in, again, this is the first row, far left column. Now I have to deal with the weight. So how do you figure out the weight? Well, the weight of a body is its mass times gravity. All right, where we're on the Earth, we would use 9.80 meters per second squared. If we're on the moon, we would use like 1.6 meters per second squared. If we're on Mars, forget the gravity of Mars, I think it's like 28% that of the Earth, but you would use that. You would use that value. So again, your weight, your mass is always the same, no matter where you are. Your weight depends on where you are. So people say, you know, they want to lose weight. What they really means they want to lose mass. You can lose weight by going to the moon, right? I mean, you can have a smaller weight because you have a smaller acceleration of gravity. So we're on the Earth, and so what we want to do is we want to try to calculate what the weight of this object is. So again, 0.100 kilograms, and then we take gravity on the Earth to be 9.80 meters per second squared. And so the weight, and again, you just basically move decimal places, is going to be 0.98 newtons. So what do you put? On the second part, you just put 0.98 because it's already telling you that it's in newtons. Now the extension. Well, again, what am I going to do? Well, again, I want this to be in meters. So again, what did I tell you? Well, I said it was 17 millimeters. Was the extension? I mean, that's what we measured, 27 minus 10. But I don't really want that though, right? I want 17 millimeters, but I really want meters because I want to do a computation with with base SI units. So I got to go to meters. So again, I want to go to meters. I divide by 1,000 millimeters in a meter. Millimeters cancel out, and I get 0.017 meters. So in my little cell over here, I'll write 0.017 meters. Okay. I'll do another measurement for you. So I picked as my second mass, I picked 125 grams. You can pick whatever you like, I guess. I mean, again, the way Dr. Edmonds wrote this lab is he kind of wanted people, he wanted people to kind of be creative themselves. Well, that's great for university physics, but I think, my thing is the college physics students need to be guided more. So I'm going to go back and share my screen again, and let's pick another mass. So there we are. Now I'm going to get my ruler out of the way. And what I'm going to do now is I have that 100 gram mass. I want to increase it. I'm going to increase it to 125. So I'm going to keep my spring constant the same. And I'm going to increase to 125. So I'm just going to hit this little right arrow here until I get to about 125. Let's see, I'm at 118, 119, 20, 1, 2, 3, 4, 5. All right. Notice now that the mass, the spring has stretched more. Why? Because I have a larger mass. The displacement vector has gotten larger. So what do I need to do? Well, I have a larger mass now. Now I'm considering, let's say 125. So I'll move, again, my little red horizontal line down to the tip of the displacement arrow. And I will again try to make a measurement. So I'll line up the 10. And what do I have here? I have, it looks like 20, so it's like 31. So 31, it's not really 31, it's 31 minus 10 or 21. So again, for 125 grams, I measure about 21 millimeters. So going back to the whiteboard, well, let's see, what's my second row look like? On my second row, I'm going to do 125 grams, which we know to be 0.125 kilograms. That's my first cell. And I got to figure out a weight Again, weight is mg. So again, my mass is no longer 100. It's now 0.125 kilograms. Remember, when you calculate newtons, you have to have kilograms and meters per second squared. Everything has to be in base SI, because a base SI unit for force is newton. And again, I'm on the Earth, 9.80 meters per second squared. When I perform this calculation, I find out the weight is going to be 1.225 newton. That's what I get. So my second column, second row, I just put in a 1.225. All right. And then what did I tell you was the displacement? I said it was 21 millimeters. All right. So over here on the far right, I now have a displacement of 21 millimeters, which is equal to 0.021 meters. All right, so that's important. So what I did is I took, other masses that I considered. I did 140 grams, ran through the same stuff. I think I did 162 grams. I'll let you do this. I did 211 grams. And I think I did 260. Those are values I chose. You can choose your own values, but those are the values I chose. And again, I did the exact same stuff. I went to the software, figured out the displacement, so over. That's for the student to do. That's for you guys to do now. So again, you can pick whatever numbers you want. Like I say, the ones that I picked, going on it. I have, we need 4 more sets of data. I picked 140 grams. I picked 162 grams, 211 grams, and then 260. All right. And so what you end up getting is a table of data. You fill that table out. All right. Now, I'm on the top of page 3. All right. So at this point, you filled out the table. Now we want to graph it. All right, so I'm going to erase this. Now I'm going to kind of just do a quick graph here for you. And I don't know, some of you guys are maybe Excel wizards, and some of you guys may not be. But Excel is an extremely useful tool. If you haven't mastered it, it'd be a good thing to do. I'm going to go fire up my Microsoft Excel, and I'll kind of show you how I would do a graph. All right. So again, I don't always do this, but in the beginning of the semester or first time we do something like this, I'm going to kind of show you, so if you're bored with this, if you know Excel like the back of your hand, well, I apologize. There's somebody in the class that may not be so cognizant with Excel. Now my question is, it's going to probably take me a few seconds to fire it up. So I'll show you Excel in a moment, and I'll show you how to do this. So I'm firing up Excel right now. So why I'm stalling. So again, I'm on the top of page 3. Does anybody have any questions right now while we're waiting for Excel?
No, I'm good.
Very good. All right. Excel has finally arrived. I'm going to click on it. So again, this is a fairly simple thing. And when you do graphs in physics, you need to be very neat what you do. You want to always be very neat, and what you kind of think of a lab as something that you're publishing. Okay, I'm going to go and share my Excel spreadsheet with you. Okay, you guys still with me?
Yeah, still here.
Good. I had a weird message pop up, so making sure something Zoom didn't decide to grow a personality. All right. I'm going to share Excel. All right, here we are. Now, turns out that, again, I want you to do your own numbers, but I'll kind of give you my number. So your independent variable is the one you kind of put first, like in a column, I'm just going to kind of do D and E, I guess. And my dependent variable I'll call F. I'm just kind of doing that for you guys. And then what numbers did I get? Again, I want to plot F versus X. I want to plot F on the Y-axis and X, the displacement, on the, actually, you know what, I'll call it Y, because it is vertical. All right, so Y is in meters. At the force is in newtons. Again, I was very careful to do that. All right, so I picked, like I said, I have, let's see here, 0.1. I mean, 0.125, 0.14, 0.162, 0.211, 0.26. All right, they get it all 0.1. Again, these are in kilograms. 0.125, 0.14, 0.162, 0.211, and 0.26. All right. Now, the corresponding force, and we did the first two. I did the first two with you. I got 0.98, 0.98 newtons. Oh, I'm sorry, my brain's not working. Never mind what I just wrote down. I'm looking for extensions. Hang on, sorry. Back that up. I want the Y value. We saw, all right, what we just saw here in being together, I had the first displacement was 0.017 meters. The second was 0.021. Remember, it was 21 millimeters. First one was 17 millimeters. When I kept doing it, I got 0.023. Again, please do your own measurements. 0.027. I got 0.035. And I got 0.043. These are my Y values. All right. So 0.017, 0.021, 0.023, 0.027, 0.035, 0.043. All right. And then my corresponding forces, my corresponding weights, if you will, 0.98, 1.225, and that's the weight equals mg. And we saw those numbers already. And again, when I did my various masses that I told you about, that I mentioned in the lab, the 140 gram mass, that goes out to be 1.372 newtons. That's its weight. The 162 gram mass becomes 1.588 newtons when you do, mass times gravity. The mass that's 211 grams, it became 2.068 newtons. And the mass that is 260 grams became 2.548 newtons. All right. And so I'm going to make this kind of pretty. I'm going to center everything. I'm going to highlight everything and center it. All right. And then what I'm going to do is I'm going to highlight the values. Okay. You highlight the values like that. And what do? Well, you go to insert in Excel. So you go to insert. And what I want to do is okay, normally it's faster than this. All right, there's your insert. And I want to go over here to the charts. I'm going to click down here and I want to create a scatter plot. And you'll notice that I have a plot that it looks like it's a linear plot. And one of the things I can do is I will label this plot. Again, you always want to label your plot. So I'll label it, I don't know, force versus displacement. plots always need a title. Let's see here. And along the bottom here, now there's a little plus sign right here that you can actually use to add axes. So I put the plus sign. I want to add axis titles. And so I want to say that, like, let's say this axis over here, the left axis, again, you always want to label your axes. I'll say force, and make sure you know what units you're talking about, force in newtons. And the bottom axis, the what we call this will be the displacement axis. It will be displacement, and this is in meters. All right, and so now another thing we want to do is, we see we have, it looks like it's linear, but it's not quite a line. But we want to do a best fit line through it. So one of the ways to do this is I'll just pick any point, and notice that all the points highlight. I'm going to right click now, and I'm going to select add trend line. All right, and what I'm going to do is you'll have a little format trend line window that comes by. You have different kinds of trend lines you can select. It's naturally defaulted to linear. We actually want linear, so that's great. We want to put a linear line, if you will, through this. There's different. You have exponential, logarithmic, polynomial, power. Well, I mean, we'll see as we go along in class. We'll have different kinds of trend lines we'll use, but the most popular one we're going to do in this class is linear. Even if something isn't linear, we like to linearize it, right? And what else I like to do here? Well, I like to display the equation. And sometimes you want to display the R value. I don't really care about that right now, but I do want to see the equation. That's what's really important to me right now. All right, so I'm going to go and highlight this, and I'm going to make it bigger because I can't see it. So I'm going to make it like, I don't know, like say size 18 or something. So it's really huge. And I'm going to move the equation kind of off to the side. I'm going to do one more thing. Is I'm going to make this plot have its own sheet. So this sheet here, I can label it as data. But I'm going to make this plot have its own sheet. So what I'm going to do is I'm going to click on the actual plot itself, right click, and I'm going to say move the chart. I'm going to move it, and I want to move it to I'm going to create I want to make a new sheet, and I'll call it chart 1. Sure. What's going to happen now is that chart's going to have its own sheet. You may have to resize a couple of things, but there you go again. So again, those axes are tiny. So let's make them a little bit. You want something that the professor can actually read. So let's kind of make this. Let's go to home. Make it bigger. Maybe like 24 or something. There you are. And then I want to. I think I highlighted it, man. Yeah, let's do select all, maybe. All right. I'll just highlight it this way, the hard way, and then go back to home and do, I don't know, maybe 20. I want to be able to see it. And then go down the bottom. This one's a little easier. Maybe do a 20 there. And I can't see the value. I can't see the axes either. So let's actually look at the axes. and go to home, make that like maybe a 20. Way I can see the numbers. I mean, I don't know, you guys are younger than me, so maybe you don't have a problem seeing these things, but all right, so we're about done with this. Let's see. Let's take it to 20. All right. So anyway, you want something that you can read. Now, notice this equation that I have. Again, you'll have your own equation. It's, everything in algebra. Remember, your algebra 1. Everything in algebra is the vertical axis is y and the horizontal axis is x, right? But we know that y really refers to f, and the x really refers to y in this particular case. So what we really have here is a y equals mx plus b relationship. So let me stop sharing for a second. And what this trend line tells you is we have a best fit curve through our data. And so that curve, your trend line is telling you what? Well, your trend line says that y is equal to, and again, in my case, I have 59.986 x plus or minus, I guess, 0.0294. That's what that says. Now, what we really know that to mean is this. My y is really the force. I mean, again, algebra always thinks things look like this. Y equals mx plus b, right? That's what. And so my y in physics really, in this particular case, really means that force, the Hooke's law force. And then what I have here is k. Remember, F equals kx is the Hooke's law. And then I don't have it quite right. Nothing's perfect. So I have a little error, plus b. This coefficient, 59.986, that is my measurement of Hooke's law, the spring constant. So what this tells me is that for this spring, my spring constant is really going to be 59.986. I mean, probably too many decimals of precision here. Newtons per meter. I have taken sets of data and I've been able to derive from that the force constant of the spring. Because I know there's a linear relationship. Now, we know that, I wrote earlier that F equals negative kx, right? But the negative is just a direction. If you want to talk about magnitudes, we don't really care about that negative. So what we really have here is what? We really have a linear relationship. What I showed you is that in reality, what it should be is I should actually go to 0. And then this data should tell you that the slope of this is k. Now, again, we should have a 0 y-intercept. We have a very, very small y-intercept, but again, nothing's perfect. We have error. And so it doesn't quite hit 0. It gets very close to it. But this is our experimental data that that allows us to get a value for the spring constant. So what you would do is you would take this graph and you'd print it out and you'd submit it with your lab. This is one of your artifacts for the lab, this graph. All right. Now, going back to page 3, that's what this is about. Now, I'm not going to go through and do excruciating Microsoft Excel lessons in the future, but what I want to do is I want to, kind of at least do it once so that you kind of know, what buttons you can push in Excel. Excel is very, very useful. So what I just did is I just did item number 5, which is really the very top of page 3. Now, again, I also did number 6. Number 6 says using your graph, determine the spring constant for your spring in newtons. Now it says newtons per meter, millimeters. I want you to do newtons per meter. Okay, class. So again, I want your spring constant in newtons per meter. Okay, so ignore what he has in the parenthetical statement there. So finding the gradient is a fancy word in calculus. for slope. You're finding the slope. Number 7 says, what evidence from your graph shows that the spring obeys Hooke's law? Well, I'd say Hooke's law is F equals kx, which is linear. The data shows a linear relationship. All right. Part 2, determining unknown masses. Well, great. What you now have is you now have a measure for your spring constant. So now that you know the spring constant, you can actually then determine the masses of unknown masses, basically. We used known masses to find the spring constant. Now that we know the spring constant, we can use the spring to determine a mass of unknown masses. We're going to do that now. I'll do the blue mass, or maybe I'll do the red mass for you, and you can do the blue mass. All right, and so let's go back to sharing. All right. All right, so let's I'll put my little ruler aside here. All right, so let's take this mass off. Let's kind of just pull it off. All right, so the spring to returns. And let's do, for instance, I don't know, we have a red mass and a blue mass down the bottom. I'll pick the red mass, see what happens to it. So I'm going to pick the red mass. And you notice that, well, it really displaces quite a bit. Whatever the mass is, it must be pretty big. Well, what is it? Well, again, I know what K is. So what I'm going to now do is determine what the mass is. So I'm going to bring my little pointer down to the tip of the arrow. And then I'm going to look at my ruler. And I'll line with like around 10. And let's see, what do I get to? I get to like 71. So 71 minus 10 is 61. 61 millimeter displacement. It's a pretty good sized mass. All right, so I don't know the mass. I do know the spring constant. And I know, and I've determined the displacement. I say 71 millimeters. All right. Oh, I'm sorry, 61 millimeters. I'm going to stop sharing. Let's go to the whiteboard. So what do I do now? All right, so I'm going to, so this is an important number here, 59.986. I'm going to kind of put that in the parking lot. All right, so I know what I've determined already in this lab is the spring constant of my spring. So K is 59.986 newtons per meter. All right, now, I don't know M, but again, what am I going to do? Well, I'm going to do that same experiment. I'm going to say, well, again, I have, I hang a mass, and I know it's displaced from equilibrium by some amount y. I know that the mass feels its weight, mg, and of course, Hooke's law opposes a force on the spring, and it's going to have an opposing force that's going to go straight up. So what do we know again? We know that Newton's second law in the y direction, sum of all forces in the y direction. Well, Hooke's law force is straight up, ky, and straight down is mg. And it's in equilibrium, so there is no acceleration. Now this time I don't know m. So I'm going to solve here. I get mg is equal to ky. Divide both sides by g. I have m equals k y divided by g. All right, and so I have some information that I can use. So now I know the spring constant, 59.986 newtons per meter. And y, well, I determined to be 61 millimeters, right? But 61 millimeters is 0.061 meters. There's KY. And divided by G, gravity. We take that to be 9.80 meters per second squared. When I do that, I find that this unknown red mass is going to be 0.373 kilograms or 373 grams. Pretty good mass. Oops, I'm sorry, kilograms. So again, I know the spring, I know it's constant from the previous work I did. I was able to measure the displacement, the vertical displacement, when I hung it on the spring, and I know that we're on the Earth, so I know gravity. So I'm able to find the unknown mass. Again, this is the red mass. I want you to do the blue mass, just like I did the red mass. You go through the same process. Part 3, I'm on page 4. We want to determine the unknown value of a gravitational acceleration. So we're actually going to leave the Earth and go to planet X. All right, I'm going to erase this. And let's, we're going to go to some place that has a different gravity. All right, going to planet X. So let's go back and share my screen. All right, so turns out planet X actually has a pretty large acceleration of gravity. So I'm going to kind of like, well, I'm going to detach the red mass. I'm going to put on a mass that, let's say, is a known mass. I picked 135 grams for my experiment. You can pick, again, whatever you want. All right, now I don't want to do the Earth any longer. I am now going to go to this table and I'm going to select, instead of Earth, I'm going to go to planet X. Again, if you look here, actually, you can kind of play around and you can actually see what happens on the moon and on Jupiter as well, or you can make your own planet. I'm going to go to planet X. All right, so notice it displaces differently, and we're going to try to figure out. We're going to try to figure out what the gravitational acceleration is now on planet X. All right, and so how do I do that? Well, again, I'm going to do another experiment. I know I have 135 grams. I'm going to go and line it up with the tip here again. All right, now, and I'm going to determine the displacement. So again, I'll line up with the 10 tick here. And what do I get? I get, that looks like 43. So 43 minus 10 is 33. So that's 33 millimeters. So on planet X, the displacement for this 135 gram mass is 33 millimeters. What's gravity? What's the gravitational acceleration now? Let's stop sharing. Let's go back to the whiteboard. Again, I'm going to go back to the equation I've derived a couple of times already, and that is that mg equals ky. Okay, now I want to solve for g on the unknown planet. So I'll divide by m. G is ky divided by m. Let's figure it out. K, well, I know about my spring. I did earlier experiments to say that has the spring constant of 59.986 newtons per meter squared. And I just did the experiment in front of you. We noticed that the displacement was 33 millimeters. Well, in meters, that's 0.033 meters. And the mass that I chose was 135 grams or 0.135 kilograms. I figure that out. Again, I want you to do the experiment with your own numbers, but I get that planet X has a gravitational acceleration of 14.7 meters per second squared. That's greater than Jupiter. So whatever planet X is, actually I think it's greater than Jupiter. Don't quote me. It's a very large planet. You know, so again, we're 9.8. Planet X is definitely a much larger gravitational acceleration than we would experience here. All right, so again, we do the same kind of thing, but this time we're looking to solve for G on another planet. All right, anyway, that's page 4. Page 5. Now we're going to go to the second part of this lab, and that's gravity. All right, so again, we're going to look at Newton's universal law of gravitation. So I'm going to erase this. We're now done with Hooke's law in the spring. I'm going to shut down the current application. I'm trying to find it. All right, I just opened up something else. All right, so I'm going to shut this down. All right, so that's down, and now I'm going to go back to the lab, and I'm going to click on the other link. To bring it up. That's a gravity link. That link is good. As I told you, the link that you have in the lab is not good. I should have changed it, but I didn't. This was a mistake that's been sitting there. I meant to change in the lab, and I forgot to do so. So I'm basically opening up. Let me share with you. All right. So where I am right now as I'm talking is, you'll notice that I'm firing up the gravity force lab. I'm going to click on the play button. You guys see that now? Do you see the gravity force lab? Anybody?
Yeah, I see it.
Awesome. All right. Click on the play button. And this one's so pretty easy. Now, again, as we said earlier, we have Newton's law of universal gravitation. I'm gonna wait for this thing to fire up, and then I'll kind of remind us again what that is, what we're actually studying. So hang on, this thing is, Zoom makes everything slower, so this thing is taking its own sweet time to fire up. All right, it's coming. There we go. All right, so there you are. I'm going to stop sharing for a second here, and let's remind ourselves what the force we're looking at. I'm going to write it in terms of just magnitudes. Again, the gravitational force, the mutually attractive force between a mass M1 and M2 is the gravitational constant, universal gravitational constant, capital G, times the product of the masses, M1 times M2, divided by the center of the center distance squared. And remember, G, capital G, is 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. So again, as far as we understand, that is a gravitational constant that is true throughout the entire universe. All right, that's what we're going to play with right now. So let's go back to the lab. All right. So again, this is a somewhat qualitative lab. You see two people, basically kind of tethering, if you will, these two masses. Now, because these two bodies have masses, they attract each other. Now you look and you say, okay, well, I on the bottom I see a mass of 100 kilograms and a mass of 400 kilograms. You notice that a gravitational attractive force is very, very small. You see 0. I mean, what I'm seeing right here, the force between F1 and F2 is 0.000000166,852 newtons. I mean, it's very small. You know, now if these masses are huge, like let's say Earth and the Moon, then that forces become the forces become bigger. You notice that there's little arrows on these. You see a little arrow for M1 that points to the left, little arrow M2 that points. Sorry, little arrow M1 points to the right, and little arrow for M2 points to the left. And these are equal and opposite forces. The force on M2 felt due to M1 is the exact same magnitude as the force of M1 due to M2. The force that you feel because of the Earth is the exact same force that the Earth feels because of you. Okay, it's mutually equivalent. All right, now, so I'm looking at here, I'm on page 5. It says, how does changing the separation of the objects affect the force between them? Well, again, we know that the forces between them it's inversely proportional to the square. So if I increase the distance, I would expect the forces to reduce. Let me make the distance bigger. Watch the force value there. It gets smaller. I made the distances larger, the forces get smaller. If I bring them together, closer together, the forces increase. You notice that the vectors get larger. The magnitudes of those vectors get larger. So again, why is that? Well, because I'm dividing by a denominator, r squared. If that center value is larger, that means I'm dividing by a larger number and I'm squaring that. That means the fraction is smaller. So the larger the distances, you know, when we move the masses apart, we notice that the force decreased. As we move the force, as we move the objects, the bodies closer together, what are we doing? Well, we have a smaller number in the denominator of a fraction, which means that the whole fraction is bigger. So the force will be larger. And it's a very a definite effect in that, you know, it depends on, it's inversely proportional to the square of the distance. So how would I answer this question? Well, I would state what I just witnessed, and I would make sure that I reference the correct equation. In science, if you always want to reference your data, you don't just write something. In science, you have to back everything up with data, facts, and one of the most powerful things you have at your disposal right here is an equation. Equations are extremely important in the universe. An equation is a statement of balance. It's a statement of two things are in balance. That's very special. So when you have an equation, this equation is worth 1,000 words. So if you have an equation, you want to get full credit, you need to reference that equation. So reference what you observed and tell me why you observed it. All right. Let's look at number 2. I'll share my screen again. Now I'm again on the very bottom of page 5. What's number 2 say? Well, what happens to the force between the objects when mass 1 increases? Well, again, I'm going to increase mass 1. It's 100 grams now. So look at that force value, 0.0000427, whatever. As I increase mass 1, what happens? I'm making the mass 1 bigger. And as it gets bigger, notice that force gets larger. I'm just increasing mass 1. Force gets larger. That's what I observe. Why is that? Again, you reference the equation. Why? Because the force is directly proportional to mass 1. You get the larger mass 1 is, the larger that force is. Again, reference that equation. The relationship between the gravitational force, you know, again, for the first part, we said that the force was proportional 1 over r squared. Well, the second part, we see the force is proportional to m1. It's directly proportional to m1. The bigger m1 is, the bigger the force. Right? So again, reference that equation. That's why you're noticing that number, that force value go up, the mutual force value. I'm on page 6 now. Number 3, what happens to the force between the objects if mass 2 decreases? Again, going back, what do? Well, we're going to go back to this lab again, and now we're going to reduce mass 2. Again, this is how you do experiments. Sometimes experiments are boring. Okay, so I have 400 kilograms. I notice that mass value. Well, let me reduce it and see what happens to the force. Well, as I reduce this value, I notice that the force is going down. Why is that? Again, it is because the force is directly proportional to m2. Again, as I look at this, I know that the force is directly proportional to m2. If I make m2 smaller, the gravitational force gets smaller. Number 4, what is the ratio? Now think about this very carefully. What is the ratio of the force on the blue object to the force on the red object? And what is the mass of the blue one is twice as big as the red object. So again, whatever the value is, I want you to help me out here. So before we go to the lab, what do you think should be the ratio of the force felt by the blue object divided by the force felt by the red object? What do you think that ratio should be? Anybody? So the blue object's going to feel the force because of the gravitational attraction by the red object, and the red object's going to feel the force because of gravitational attraction by the blue object. What's the ratio of those two forces? Well, it's a mutual force. The blue object feels the force F, given by G m1 m2 over r squared. The red object feels the exact same force, given by G m1 m2 over r squared. They feel a mutual force. So the force felt by the red object divided by the force felt by the blue object, all those forces are the same. Their ratio is 1. The ratio is 1. I mean, they feel the force of the blue on the blue object, gravitational force on the blue object, because of the gravitational attraction from the red object, is exactly equal to the force on the red object as a gravitational attraction by the blue object. They feel the same force. The force that you feel because you're on the Earth is the exact same force the Earth feels because you're on it. Right? It's a mutual attractive force. The magnitudes are the same. And to show you that, and it doesn't matter if you make one mass bigger, it doesn't matter, right? So for instance, if you notice those forces, those two forces, force on M1 by M2 is absolutely the exact same value as the force on M2 by M1. It's a mutually attractive force. So if I decide, hey, I'm going to go make M2 a lot bigger, again, as I'm making M2 bigger, notice those forces are still equal and opposite. It doesn't matter. I can make it the mass of the Earth if I want to. Those forces are still going to be equal and opposite, irrespective of what the relative masses are. They're still going to feel the same mutually attractive force. 5 says, what's the direction? What direction is the gravitational force acting on the object? Well, notice those arrows are pointing inward. M1 points toward M2. M2 points the force vector from M1 points toward M2. The force vector from M2 points toward M1. They point toward each other. Again, they are equal and opposite. Now this one's interesting. Part 2 on page 6. It wants you to define the dependent and independent variables in the constant. So again, this gets back to more mathematical lingo. So again, let's look at this equation. Now let me kind of go back and just give you some general equation. Let's say I give you y equals 3x. Let's go back to algebra. Y equals 3x. Well, again, the variable on the right side, and if I were to let's say graph this, it'd be something like this, right? Here's x, here's y, and it's a slope of 3, whatever. And you know, if I were to graph this, I'm free to choose on the right side whatever I want for the variable. But once I make a choice, if I say I want to make x equal to 1, once I make that choice, I have now forced a value for y. Because of this rule, if I say, hey, let x equal 1, well, now y is now confined to be 3. If I say, hey, let x equal 2, well, now 3 times 2 is 6, right? So anything on the right side, we would refer to x as an independent variable, because I can independently choose whatever value I want. But once I choose a value for x, I have now forced a value for y. So then y would be called the dependent variable. And that's going back to algebra 1. Let's look over here. Well, in this particular relationship, I want to know what are my variables and what's the constant. So again, anything on the right-hand side are variables that I'm free to choose. So my independent variables, let me ask you, one of you guys, what do you think my independent variables are? Anybody? You guys with me? This is an algebra 1 question.
Yeah, I'm with you. Would the mass be the
Yeah,
dependent?
M1. Yep, M2. Anything else?
The force.
Force would be dependent.
Okay.
There's one side, so I have one more independent variable.
Distance.
R. Yep. Well, I am free to choose M1, M2, and R, whatever scenario. I can say Earth, Moon, and whatever the distance, or I say Sun, Moon, and 93 million miles, whatever. I've made that choice, but once I make that choice, I have now forced a value for the force. And then there's one other thing, and that's the constant. What's the constant here?
That would that be the value of G?
Capital G, absolutely. Very good. Thank you, Eduardo. So that is the value of, so that is what we're looking for. We're looking for a relationship. Again, we're describing physics. One of the beauties of the universe is that we actually can describe physical phenomena by mathematics that humankind can understand. Humans can understand this mathematics. And it's amazing that the universe obeys it. All right. And so again, this is something you learn from algebra. And yet we're able to apply it to a physics problem. That's amazing. Okay. I would say on quantitative reasoning, one that says is create a table for the 10 data points. I just cross that out. So I would say cross that out. That's just a lot of extra work. So again, right below you have a dependent variable, independent variable, a constant. Let's see if you can actually see this. Maybe not, but anyway, there's a number 2, create a table for 10 data points and graph the result. I I always cancel that. I just cross it out. Don't do that. And also number 3, repeat the varying mass and force experiment, changing the second mass. Again, that's just, I think you get the point. So I'd say cross that out too. So again, under part 2, quantitative modeling, do part 1, which we kind of pretty much did here. Cross out number 2, cross out number 3. All right, and the last part of this lab are the queries. So again, I want you to give me full explanations, for what's, what you're seeing. So like number 1, explain why varying the second mass had the same effect on the force as varying the first mass. Again, why is that? Well, it's because they have the same relationship. The force is directly proportional to M1. The force is also directly proportional to M2. So varying either of those masses will have the same relationship. Again, I want you to put this in your own words. But again, I want you to back it up. And what are you going to give me? You're going to give me an equation to back it up. Again, you need to give me evidence. We don't just state something. You always have to back it up with evidence. It's science. And a beautiful piece of evidence is an equation. Query 2. What is the relationship, proportionality, between mass and force? What happens to the force if you double the mass of the blue object? What happens to the force if you then triple the mass of triple the red object's mass? I want you to think about that. Again, I want you to tell me, okay, what's the force? I'll do one of them, and I want you to do the second part. So again, what's your line of reasoning here? Again, this is a University of Physics type lab, so I'll do a part here for you. So let's just say I have a situation that I have M1, I have M2, and I have a center to the center distance. R. All right. And what's the force? Well, I'll call it F1. F1 will be G M1 M2 divided by R squared. Again, that's the magnitude. Well, what am I telling you to do? We'll just say this is the blue. We'll call this the blue object and the red object. So I have M sub B and M sub R. M sub B, B for blue, R for red. All right. Now, what do I want you to do? I'll do the first part for you. Okay. What happens? That is the relationship, right? And what's the relationship between the mass and the force? Again, this is the relationship. It's Newton's law of gravitation. What happens to the force if you double the mass of the blue object? What happens? Well, let's just say now that I'll have M sub B becomes, I'll call it M sub B prime, new force. And it's basically twice what it was before. I'm doubling the mass of the blue object. And so what am I going to do? Well, I'm going to have a new force, F2. And it's going to be G M sub B prime, my new mass, M sub R, I haven't touched the mass before, divided by R squared. Well, what is M sub B prime? Well, it's 2M sub B. So that's G times 2M sub B times M sub R divided by R squared. And I can pull that 2 out front. That means my F2 becomes 2G M sub B M sub R divided by R squared. And hey, I know what that is. G M sub B M sub R divided by R squared. That's just F1. So I could now write that F2 is 2 times F1. I've proven that if I double the mass, I double the force. F2 is twice what F1 is. What it wants you to do now, it wants you to kind of do the problem again, but now you're going to consider an M sub R prime equaling 3 M sub R and kind of tell me, now you have M sub B prime, now you have M sub R prime. And what now is going to be a relationship between F1 and, you'll basically kind of go through the same logic. And I want you to tell me that at the very end that after you go through the logic, blah, 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 you're going to tell me that F2 equals something, I'll call it alpha, F1. And you need to tell me what alpha is. By kind of going through the same logic. I did the first part for you. So now you've doubled the blue mass. Now you're going to triple the red mass. And I want you to tell me what that value is going to be. Before, when I just did it, that value was 2. Your value is going to be something else. I want you to tell me what that is. I want you to prove it to me. That's number 2, query 2 in a problem page 7. Number 3. What is the relationship between distance and the force of gravity? What happens if you triple the distance between the objects? All right, and then halve the distance. I'll show you how to triple it. All right, so again, I'm going to go back. And this time, I'm going to leave the masses alone. And I'm going to consider another R, I'll call it R prime, another value of R prime. But this time, I want to triple what the value of R was before. What happens now? Well, I'll create an F2. That's going to be G M sub B M sub R divided by my new distance R prime squared. Well, hey, what is R prime? Oh, it's 3R, right? That's going to be G M sub B M sub R divided by 3R. Be careful. Quantity squared. All right. Well, a square of a product is a product of the square. F sub 2 will be G M sub B M sub R divided by 9, 3 squared, R squared. And let me pull the 1/9 out. That gives me 1/9 G M sub B M sub R over R squared. Oh yeah, and I recognize that. That's F1. So when it means that I find out that I have made the force much smaller. F2 is now 1/9 F1. Now, what I want you to do in the second part is I want you now to consider this. Okay, now halve the distance and go through the same logic and tell me what that number is. Okay, show that to me. On number 4, query number 4, I don't really understand what he's asking for here. So I would just, what I did last time, I just crossed it out. So cross out query number 4, don't do it. And that is it. That's the lab. All right, does anybody have a question at all? I mean, that's the whole kit and caboodle.
So when is this lab due?
Okay, so next week is spring break. Very good question. Thank you, Eduardo. Next week is spring break. Normally labs are due the following Friday, but because it is spring break, well, you kind of have, well, you have a double positive here, don't you? Because you have spring break, and then you come back and take an exam. This lab's not due for about 3 weeks. So let me get my cell phone out and make sure I can do this right. So yeah, I'm hoping everybody listens to this lecture here. All right, so you come back 19, and then March 26, you take an exam. So it looks like this lab is due April the 2nd. So again, normally it would be due next Friday, right? But spring break. So that's Friday, March 19th. Then it would be due when? March 26th. But that's the week of exam 2. So yeah, I don't want you forgetting about this lab. Yeah, this lab would then be due April 2nd. So yeah, so very, Excellent question, Eduardo. So let me make sure, hoping everybody has stayed with me long enough who is watching this video. But this lab will be due Friday, April 2nd. The lab due. So Hooke's law. I guess I'll write an email out when my blanket email works again. Hooke's law and gravitation lab. Due on Friday, April the 2nd. We're already getting into April, believe it or not. All right, thank you for that question. Any other questions?
No, that was my only question.
Okay, Sarah, how about you?
I'm still trying to work out query number 2. You kind of lost me on that one, to be honest.
Oh, query 2? Let me look at it again. Spend a little bit more time on it if you like. All right, query 2. What's the relationship between the mass and the force? What happens if the force, you double the mass of the blue object? What happens if the force if you triple the red object? I mean, well, okay. So did you understand what happened when I doubled the blue object?
Yes.
All right, well, I'll just do it, I guess. All right. Too easy. All right, so force is G M1 M2 over R squared. But again, I want to actually say that's F1. All right, that's the original. But what I'm going to do is I'm going to say, hey, I want to have M1 prime go to, I want to double the, oh, I'm sorry, blue and red. Blue, red. I want my new blue mass, M sub B prime. The prime just denotes the new mass. I want it to be double what the original blue mass was. And this time I want to do two things at the same time. I want my new red mass, M sub R prime, to be triple what the red mass was originally. All right, I think that's what they want. Now, all right, so in that case, if I have a new mass M sub B prime and a new mass M sub R prime, I have two new masses. So I would have another force, so I'll call it F2. And it's going to be G, and then these new masses, M sub B prime, M sub R prime, divided by the same center to center distance R squared. Okay, that's my new, I mean, I've doubled the blue mass, and tripled the red mass. Well, I happen to know relationships between the new masses and the old masses. All right, so I can write this as G. Instead of M sub B prime, it's really 2M sub B. And for M sub R prime, well, I can write that in terms of the original stuff too. 3M sub R over R squared. Again, I'm writing the force in terms of the original variable. Now I have these constants. I can just use the commutative property of multiplication. I can pull everything out. 2 times 3 is 6. So F2 now becomes 6. G M sub B, the original mass, M sub R, the original mass, divided by R squared. Oh, and by the way, that combination, I know what that is. That's my original attractive gravitational force. That means that, setting all this stuff up, the new force, when I make these changes, doubling the blue mass and tripling the red mass, it becomes 6 times the original gravitational force. Right, so I made 2 changes, but how does that compare? And just understanding that this is really F1 right up there. So I'm just really writing in a fancy way what the new gravitational attractive force is compared with the original one. Is that clear?
A whole lot better. Thank you.
Sure. I mean, one of the things in physics is you want to always have kind of good ways to do like official proofs. So this is kind of a proof that, that of how your forces compare. Any other questions?
No, I'm good now. Thank
All right, so I hope this video actually saves. I've been having all kinds of technical difficulties today, so. All right, well, thank you guys for showing up, and I'll put this lab on YouTube, and I'll send the link later on
Thank
Blackboard.
you.
You bet.
Thank you. Have a good
You too. Have a good spring break.
Thank you. Have a good night.
You too. Have a good spring break.